Saxon Advanced Mathematics. Lesson 35. Pure algebra today. John chops this up into 3 different topics, but they're all kind of related and flow from one to the other really well. So there aren't any, big jumps going from one part of your brain to the other. It's all kind of sitting together. Okay, what we are going to talk about first is a change in coordinates. Now, I'm not going to draw the grid beneath it, but here are 2 points. We're going to call, excuse me, I'm choking with excitement. I can't wait to tell you about this. We're going to call these 2 points A and B. Here's the distance between them. A is -7, 4, and B is 3, -2. They're kind of in the right place if I drew the grid on here, but I didn't want to get into making it to scale and putting a bunch of lines in here. So that's why I left it simple. When we want to find the change in these coordinates, we have a simple, I hate to even call it a formula. We take the final point and we subtract from it the initial point. Now, final means like the ending point, and this means the starting point, but we're going to use this terminology because we're going to use it in several parts of this lesson, okay? Now, here's the thing about changing coordinates that's a little bit tricky. We get to choose the direction. So when we're measuring the change in coordinates, it can be going from A to B, like in this direction, or we could go the other way. It could be from B to A. We could be going in this direction. And the way that we measure the change will be slightly, will give us different numbers ever so slightly. We're going to do it and you'll see. For depending on which direction we're going. So let's start with the scenario of going from A to B. All right? In this case, A will be the initial and B will be the final. All right, so what would that look like? Well, for the x values, right? We're looking at the x values. That's the first number in the pair. We're going to take the final value. We're going from A to B, so that would be the B value of 3. And then we're going to subtract from it the initial x value, which is the A value of -7. Notice how I use the parentheses so I don't make my head crazy. What that tells us is that the change in x is going to be +10. Easy enough, right? Our y value, final is B, initial is A. We want to take the final, so it's B minus A, -2 minus 4. I'm putting this bucket in just so you can clearly see the value versus the minus sign. -2 minus 4 equals -6. Okay, so there are the changes in the coordinates of x and y as we go from A to B. But what if we want to go from B to A? We want to go in the opposite direction. Well, that means that B is the initial and A is the final. So when we go to calculate the changes, we're going to use these things in the opposite order. So we take the final first. The x value of A is -7. And then we're going to subtract, because that's the formula. And then B is the initial, this is the initial value for x, and it is 3. So look what happens. The change in the x value is now -10. Oh, interesting, right? And I bet you can guess what the change in the y value will be. Again, we're going to do final minus initial, so that will be A minus B. The A value is 4 minus the B value is -2. So that equals 6. So look what happens. The changes are the same number, but the opposite sign, which makes sense. Because if we're moving 10 units as we go this way, then we're moving -10 as we go that way. Same thing for this with the y. If we're moving 6 units down as we go from A to B, then we're moving 6 units up as we go from B to A. All right, so this shows us how order matters. And we're going to use this in our examples, which are not what you would expect. These problems are a little surprising, not hard, but just weird. It's not the way John usually asks us questions. Given the points P1, which is -3 and 2, and P2, which is -4 and -5, what do we represent by A, -3 minus -4. John did not put these parentheses on. I just automatically did, but you can pretend they're not there. It doesn't change the problem at all. And then B is -5 minus 2. Okay, so what he wants to tell us is it a change in X or Y? And is it a change going from P1 to P2 or vice versa? Okay, so let's get our formula handy. It is final minus initial. Again, that's not exactly hard. It's not much of a formula, but it is backwardsy feeling. So you have to keep your brain on straight. Okay, as you know, these are the X values and these are the Y values. So let's look at A. We're using -3 and -4 as our values. So we look here and we go, okay, well that tells us we're measuring the change in X. So that's the first part of our answer, is which are we changing, X or Y? And then we have to decide, are we going from P1 to P2 or are we going from P2 to P1? We know that the final value is the first one, so that tells us that we're going from P2 to P1, right? Because this one was written first as we calculated, and that's the final one. So that means P1 is the final location. P2 would be, no, I said that wrong. Wait. This is correct. I'm turning myself backwards right now. Let's do this one. We see it's -5 and 2. That means it's the change in Y. And -5 is the final point. So that means we're going from P1 to P2. That's correct. And sometimes it helps if you put, okay, -3 is P1, and -4 is P2, and -5 is P2, and 2 is P1. Now we know that the first one is the final one, so we're going from this to that. That's what I wrote here. From this to that, and that's what I wrote here. So if you feel yourself getting scrambled around a bit, just put more details into how the numbers are behaving. You know what I mean? Label things and it will help you. And this is the correct answer for both of these. Yay. And I think 35.2 is the same setup. Ready? This one says, if the coordinates of P1 are -3 minus 2, and P2 is -4 minus 5, what do we represent by A, that calculation, and what do we represent by this calculation? John puts buckets on the second number, which makes sense to me. That first number we're not going to confuse. If it's minus, the minus sign just chills there. The second one is where we really need to be careful because it follows the minus sign in the formula. Okay, once again, let's get our bearings. These are the X's, these are the Y's. That can be helpful. And let's label, let's figure out which one of these. This is the change in X, right? Because minus 4 and minus 3 are the X values. So I'm going to write change in X. And this one is the change in Y's. I can see minus 2 and minus 5. So that's the first part of my answer, is to decide which variable. Now we have to figure out which one we're going from and to. Minus 4 is P2, minus 3 is P1. So that means this is final. So I'm going from P1 to P2. You can write that with an arrow, that's fine. You can write it with the word. This is correct. And then the same thing over here. Minus 2 represents P1 and negative 5 represents P2. So that tells me that it's going, this is the final point. So it's going from P2 to P1. Did I get it right? Yay! I'm always happy when I get it right. I hope you are too when you're doing your homework. Okay, so that's what we're looking for in this style of problem, is which variable are we changing and then what order are we changing them in. And it's confusing because the formula is going final to initial, but we want to write initial to final. So we have to like flip the order. So that you just have to keep your head on straight. It's not particularly hard. All right, that is the first part of our lesson. Keep this final minus initial thing in mind because we're going to use it again. Okay, this is a calculation we learned right at the end of last year. It'll look familiar. We didn't have a whole lot of time to practice it, but you'll probably remember. And we're going to use this thing again, final minus initial. I think we called it something slightly different in the book last year, which probably I should change and make sure I use that terminology. These are a very specific kind of problem. I'm not sure that this really is a good title for it, but whatever. What is the number whose graph is 2/3 of the way from 3 to minus 7? Okay, so I'm going to write it down just so we can see it. What is the number that is 2/3 of the way from 3 to minus 7? Now, last year we drew a number line and fiddled around with that. I don't want to do that again because this problem isn't so easy and perfect to do as the first one we did last time. What we want to do is just work with the formula. What we do is we take the initial number and we add to it, well, I'll just write it and then just barely squeezed that on at the end, didn't I? This is our formula. Notice that right here, this is our change in coordinates calculation. So we're taking that formula and we're building it into a bigger formula. This is how we find the change in a number. Make sure you put that wherever you're putting your formulas. Please put your formulas into some sort of organized place. A piece of paper, a couple pieces of paper, a notebook, writing it inside of your homework. And please do keep your formula pages until you have finished your mathematical career in school and you're moving on to real life. It is so useful to have all those formulas in one place, and it is so annoying for you, not for me, for you, when you don't. So please figure out a system that works for you. Again, I think the easiest thing is to write them on the covers of your homework books. But you know what? Then you have to remember not to throw out your homework books, which I want you to keep your homework books anyway. Anyone who is homeschooled, working outside the supervision of traditional school districts, should keep their proof of their work until they get their degree from not the current place they're studying, but the next. So keep all of your stuff not only up until you graduate from high school, but after you graduate from high school, keep it until you get your next degree for sure, because you want that second graduation to cover all of this. If anybody should ever question your math, if anybody in college should ever question your math in high school, you want to be able to back it up. So keep your books. If you're not good at staying organized, have your mom figure out a way to do it for you, but don't throw this stuff away, please. Keep it. Okay, so now we've got a problem and we've got a formula. Now we just plug it in. Remember, this is our initial number. From blah to blah, this is our final number. And this is our fraction. All right, so we're going to say that this is 3 plus 2/3 times minus 7 minus 3. That doesn't look that bad, does it? This becomes 3 plus 2/3 times minus 10. Let's change this one. Let's multiply this by 3/3 and make it 9/3 so that we can add. Here, I'm going to write it down here. 9/3 plus minus 20/3. And final answer is this is minus 11/3. So if you're moving from 3 to minus 7 on a number line and you want to go 2/3 of that distance and then stop, this is the number where you stop. I don't know where you would need to know that, but so be it, Jedi, right? It seems like it's got a practical everyday application, but I can't think of what it is. Okay, example 35-4. Now, instead of writing it all out so much, I'm going to show you how you can do it for your homework. Remember, our formula is fraction, it's initial plus fraction times final minus initial. I'm not going to keep writing out final and initial because we'll be here all day long, which sounds really fun to me, but probably not to you. Okay, this time, instead of writing out the whole problem, I'm just going to write fraction, initial, and final. And I'm just going to find these values in the problem and go from there. This is 35-4. What is the number that is 3/7 of the way from minus 4 to positive 9? And John puts an actual positive in the book. That's quite unusual for him. All right, so it's worth pointing out that we can be going in either direction. We can be going from left to right on a number line, or we can be going from right to left. We don't have to worry about that. As long as we just write the values in right, our calculation will be fine. But just remember that that's going on. Sometimes we'd be going this way, sometimes we'd be going that way. It just depends on what values we're getting here. All right, let's write it out. So it's going to be minus 4 plus 3/7 times 9 minus 4. I don't want to put double buckets around that, but I'll just make sure I'm really clear. I'm going to have to end up adding that little puppy dog. All right, so that becomes, I'm going to immediately change this. It's going to be minus 28/7 because I know I'm going to have to combine it. Plus, this is 9 plus 4, this is 13. 13 times 3 is 39/7. And so my final answer is positive 11/7. over 7. That's the right answer. All right. 34.5. This is the last one. Or 35.5. Sorry. I can't talk. I can do math all day long, but sometimes speaking is too much for me. This is another problem like these. Then we're going to go to our third subject. Find the number. Oh, wait. First, I want to write this. Fraction, initial, final. I do not write F for fraction because it's too confusing, because then we would have 2 F's. All right, find the number that is 5/11 of the way from 3 1/8. If you want to convert that to a mixed number as you write it down, that's fine. To minus 3 5/8. All right, well, at least they're both 8s. I feel good about that. This is an 11, so things are going to get crazy in the fractions here, but we can do it. Okay, let's change these into impropers right away. 8 times 3 is 24, plus 1 is 25. And then again, this is 24, 29 over 8. Those go kind of downhill a little, but you got it. All right, ready? Let's just write it down here. So, initial number is 25 over 8 plus the fraction times the final number minus the initial. Except wait, this is negative, so I need to make that negative. And then this is negative from the formula, but it's a positive number. Okay, I got that right. So this becomes 25 over 8 plus 5 over 11 times, ooh-wee, what is that? 54 minus 54 over 8. Ay, 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 ay. I could probably reduce this. I mean, for sure I could because they're both even, but I'm just going to leave it because I will be able to adjust this 8 by multiplying it by 11. I'm not going to worry about making it smaller. Okay, so we need to multiply 54 times 5, right? 270. So this is going to be minus, I'm going to just draw a line through this. It's going to become minus 270 over 88, right? 5 times 54 is 270. 11 times 8 is 88. Positive and negative, so this goes negative. I cross this out so I don't have to rewrite it again. All right, now I'm going to have to multiply over here times 11 over 11 so that this becomes 88 as well, right? So this will become, let's see, 25 times 11. Remember, you can do that pretty easily just by staggering the 25s and adding them in your head. So that's 275 over 88. Now that's adjusted. So what we've got, I'll rewrite just so we can see it. 275 over 88, which is this, plus a negative 270 over 88. Well, you got to give it to John. He makes the numbers come out nice. And we get 5 over 88. And remember, that's the number that is 5/11 of the way from this to that. If that makes you happy. John doesn't ask us to graph these or do anything like that. We just calculate the number, and that's right. But you could, if you wanted, right? We could draw a big old number line, and we could put this number at one end and this number at the other end, and then we could start moving from this one toward that one and stop at that number and say, look, it's 5/11. It's almost halfway there. Okay, that's the right answer. That's all we need to do for this name of a number business. The last part is also something we touched on last year, and it is the distance formula. Now, this is similar to what we started with. Remember, I want to go back to our original picture so that I can show you how this is similar to what we did before, but also different. When we did the change in the coordinate, what we were finding is the change in the x as we move from one point to the other, and the change in the y. We found the change for each coordinate separately, and we said that the direction that you're going matters, okay? In these, what we're finding is the length of the line between the points. So that's kind of a combination of the change in the x and the change in the y, right? We're not separating those into two separate data points. We're combining them and saying we want to know the length of this line, not the change in the x and the change in the y. That's kind of like the slope, isn't it? We don't want that. We want the distance from here to here, and in this calculation, the direction doesn't matter. Okay, there's none of this final and initial because we're not talking about the movement, we're talking about the distance, all right? So that's what makes this formula different than what we were doing in the beginning. Now, what's cool about this is that you already know how to do it. We've got this distance that we're trying to find, right? And you know what I'm going to do? I'm going to draw another picture because I want it to match what John's showing us in the book, because there's a reason for that. All right, the points he's giving us this time, let's draw a little grid action here, shall we? We are going from this point, which is -3, 4, to this point, which is 4, 2. And again, we don't want to find the changes in the x or the changes in the y. We're not talking about moving from one to the other. We're saying, just tell us, how long is this line? Oh, pretend it's perfect. Kind of went off target there. We want to know how long the line is. Well, we have a really useful tool for doing this. Let me show you what that looks like. Let's imagine that we draw, oh, my picture's so off here. We are drawing a right triangle that connects those 2 points into a right triangle. And you know what the cool thing about right triangles is? We can use Pythagorean theorem to solve for the lengths, right? Now, and we can also use, if you can do this mentally, we can flip the Pythagorean theorem around to basically say, take the square root of both sides, and there it is, exactly how it is to calculate this distance, right? Now, the only problem is we don't have the A or the B, right? Clearly, we're trying to find out the C, but we don't know the A or the B. But we can find it really easily. We can do it in this picture, if I would have drawn it perfectly. Let's do it this way, this one first, okay? How far did we move along the x-axis? Well, we started at -3, and we went up to +4. So that is 7 units, right? And so let's call this A. So A is equal to the change in the x coordinates. Okay? From from minus 3 to 4 is 7 units. And then what about this b? B is the change in the y's. Squishy to squeeze it in. So here we can see we went from 2 up to 4. We don't have to worry about direction because we're going to be squaring everything. And so positives and negatives we don't have to worry about in terms of that whole, like which is the initial and which is the final. Because as we saw, the numbers stay the same. Remember that at the very beginning of this lesson, we showed that depending on which direction you're going, the number stays the same. The sign just changes. And since we're going to be squaring everything, we don't care. So to find this value, which we've been calling C, but we're now going to call D for distance, we simply take the square root of the change in the x-coordinate, which is 7, and add to it the change in the b-coordinate, which is 2. Makes sense? And we will get our answer, which is going to be what? 49 plus 4. So the distance is the square root of 53. Okay? Now, the question is there an easier way to do this? Because we had to do a lot of drawing and fiddling and fussing around. And the answer is yes, there is. It revolves around a new formula, but the new formula is a dream. The distance is equal to the square root, just like a square root here, of the change in, I did it in the opposite order. Well, just pretend it's the same. It doesn't matter because we add them. The change in this is the y coordinates and the change in the x coordinates. There's a reason why I want you to memorize it this way. I'll talk about that in a minute. But do you see that the change in the y coordinates is simply that? And the change in the x coordinates is simply that. So this formula is really just the Pythagorean theorem set up so that we don't have to find those distances. We can just plug in the points. This is the distance formula, and it is heaven. It's going to help us do problems like this much faster. All right. You'll notice that this looks a lot like our slope formula. Remember, we use this to find the slope when we're given 2 points. That's why I like to use this form of the distance formula. The distance formula comes in about 4 different derivations. They all work exactly the same, but in order to memorize it, I like to use this one because it looks so much like this other formula that we already know. All right. One other thing I want to say about this picture. Well, I remember when I first saw this, I was confused because I thought, why don't we draw the triangle this way? This makes more sense to me, is to draw the triangle like up and over and have the distance part down below. And I could not understand why we didn't do it that way. Spoilers, you can. If that triangle makes more sense to you, you can look at it that way. I've since gotten used to drawing my triangles to go down toward the x-axis, because you know in trig we always make the triangles go down. So it seems more normal to me now, but if this weirds you out and you want to draw the triangle up, you can. It'll work out exactly the same. This will be 7, this will be 2. All right, so what I'm trying to show you here is that we can use Pythagorean theorem to solve this, but it requires us to do a little bit of extra calculations. But the distance formula is really just the Pythagorean set up so that we can go directly from the points to the calculation, and we don't have to stop and find the sides of each leg of the triangle that is formed from this. We can just go directly into the formula. Let's use it. You're going to want to multiply it. I mean, memorize it. Oops. But let's write it down up here. Remember, it starts out looking like Pythagorean. Something squared plus something squared, right? That is very Pythagorean. Then we use that slope formula to fill in the blanks. All right, so there it is. It's not too hard to memorize, like I said. And it allows us to use Pythagorean theorem to solve for the hypotenuse given the legs when we don't know the actual length of the legs, but we do have the points. Okay, here comes our problem. 35.6, ready? Use the distance formula, ta-da, to write an expression that gives the distance between points 4, 2, and some other point x, y. Okay, that's a comma, not a 1. All right, so what John's doing is he's asking us to set up a formula that we could use for some other bigger calculation if we so wanted. We're not going to get a numeric answer to this, but we will get a formula that's set up and ready to go for some other type of problem. P.S. This is our last problem. So what we do is we just say, okay, let's make this, the x2, y2, and this the x1, y1. It doesn't matter, but I usually just make the first one the 1s and the second one the 2s, and then we're just going to use this format. We can set it up. Exactly like that. That looks very Pythagorean. And then we use the change in the coordinates to pop in here. So y2 is y minus 2. That's y1, right? I'm flicking these two values. And then over here, x minus 4. Beautiful. Now, if we were trying to measure a number of different points and their distance from this point 4, 2, we would have a formula set up and we wouldn't have to calculate it every time. We could just say, okay, pick a point that we want to compare and find out how far it is from 4, 2. Let's say that you had a map of your neighborhood. You'd graphed it out and your house was at location 4, 2. It was at that coordinate on the graph, right? And then you were picking different places all around your house in the neighborhood that were on this map also, and you were trying to find the distance from your house to the different places, right? And you wanted to put in a couple different stores and houses and parks and stuff. This formula would let you use it because you've already got your house's coordinates plugged in, and then you could put in the coordinates of the different stores, parks, wherever you want to go, your friend's house, and you could find the distance using this. So that's what that would be helpful for. Oh, I see I did something wrong. Let me fix it. It's a little mistake and it doesn't change the world here. The problem actually is -2 here. So the only thing that's going to change is here when I plugged it into our formula, the minus sign in the formula is going to go positive, isn't it? So let me fix that. When I looked at the answer, I realized, oh, I'm off there. I just dropped that minus sign when I copied the problem out of the book. Story of my life, right? So we just flow it through, but we use the formula in just the same way. This is the correct answer now. And guess what? We're done with lesson 35. Yay! Congratulations, go do something fun. Your brain must be tired. Take care of it. Goodbye.